Okay, welcome. In this video, we'll do some further exploration of simple linear regression. So we will draw predicted values and their 95% confidence band. We'll make a prediction of a new observation. We'll fit a Loess curve to the data, and we'll compute different kinds of residuals, and we'll conduct different tests for regression diagnostics. All right. First, let's read in the data set and then do a little inspection. So you can see it's a pretty simple data set with two variables, glycol and pH. Glycol is the dependent variable and pH is the independent variable. So before we fit the regression line, we can generate the scatter plot for these two variables to take a visual of their relationships. Okay, so it's look like that. Not sure what to make of it, but it's here. And then we can just start fit a simple linear regression. First, we just let's just assign like pH and glycol to the x and y. Perform linear regression, very simple, just use the function LM. And after the model is fitted, then we can get fitted values, and then we can also get their confidence intervals using our function predict. So predict model interval equal to confidence, and level equal to 0.5. And store that into the object fitted. And then we can plot the scatter plot with fitted line and confidence interval bands. Now, here it is. It looks like this. So if we want to be fancy, we can even do some gray coloring, shade the area using the polygon command. But now the fitted line is covered, so let's bring it back using the AB line command. Okay, so that's the first part. And second part is prediction of new observations. So basically, once we have fitted the model, then given the new x value, we can predict the corresponding y value. Okay. All right. So here, let's just say the new x is 7. And then to predict the y value corresponding to 7, we use the command predict. So the syntax is predict model and new data equal to data frame x equal to new x, interval to confidence, and level equal to 0.95. So as you can see, we can predict y's for one x, and if we have multiple x's, we can place them into a data frame. Then the predicted y will be a data frame. Let's do that. And then we just print out the predicted value and its confidence interval. Okay, so, all right. As you know, the LM function has a default plot function which will generate the 4 basic residual plots. Let's just do it again. And you see these 4 types of residual plots: residual versus fitted, QQ residuals, scale, location, residuals versus leverage. I covered this in a previous video about how to fit a simple linear regression. Okay, so if you think the true relationship between x and y is not really linear, and you want to explore data-driven kind of curvilinear or nonlinear fit, you can use the function Loess, L-O-E-S-S. Okay, so it's a non-parametric smoothing method for fitting a curve. Okay, so let's use this command, fit it. Similarly, we can get the predicted value from it. And then we can plot the data points and fit line. And let's bring back the linear regression line also. So you can look at it. Overall, it's still trending down, but it has a little bit ups and downs compared to the straight line fitting. Okay, so now the R function residuals will calculate raw residuals. So if we do that, it can be calculated, and the fitted values can be computed using fitted command. And then we can calculate standardized residuals using the R function R standard. Okay. And then there's another type of residual called the studentized residuals, or also called jackknife residuals. For that, we need to use a library called mass. Okay, so let's load library. And then you can use the function studres to compute the studentized residuals. And we can generate different residual plots using these different types of residuals. And then those residual plots are informative about the model fit. Okay, so we're not going to do those here. This is just showing how to compute these residuals. Okay. Another one is Cook's distance for identifying outliers in the data. You can do that use Cook's dot distance. Okay. And then you have the hat value also for the leverage values. You can use the function hat values to calculate those. And then you get the df beta, just looking at the influence of individual observations. You can use the df beta function to do that. And then there's some other variants of that. You have df beta hat. You can use the R function df betas and type equal to hat. Okay. And then you have the df beta star. You can use the df betas, then type equal to star. So another important diagnostic is called the variance inflation factors, VIF. This is what you need to look into if you worry about the collinearity among independent variables. And for computing VIFs, we need another library called CAR. Okay, so if you load that, and then you can just use the function VIF to compute the VIF values. Oops, so here our complaint said VIF requires 2 or more X variables. Because we're doing a simple linear regression, we only got 1 X variable. So it cannot be done here, but you've got to have 2 or more X's, the independent variables. But you can do the compute the VIF value using this function. And next, we're going to conduct a few hypothesis tests designed for regression diagnostics. One is the Broch-Pagan test for heteroscedasticity. Okay, so that we need the library called the LM test loaded in, and just using the BP test. And there's another one called the rainbow test for linearity. You can use the linear hypothesis function to do that, test equal to F. And then the Shapiro walk test for normality of the residuals, you can simply just call the Shapiro dot test function. And then there's the Durbin-Watson test for autocorrelation. Again, you need a library called a CAR. Let's load it again, and then you use the Durbin-Watson test. So get that test result. And there's also an outlier test. You can use the R function outlier test to calculate the result for the outlier test. And then we can just print out all the results here. Also, there's a residual plots command will generate these two residual plots. Okay. So in this video, I just showed you how to compute all these regression diagnostics or conduct hypothesis tests. We'll cover what exactly these diagnostics are and what they are for in another video. Okay, thank you.